This is Physics 102B, Chapter 24 homework solution, starting with number 17, a hydrogen atom transitioning from the n equals 4 level to n equals 2. This results in the emission of a photon with what wavelength? We're going to use the Rydberg equation. Here it is. 1 over the wavelength is the Rydberg constant times 1 over j squared minus 1 over k squared. We're always going to take j being less than k, therefore we'll get always positive answers. The Rydberg constant comes in two forms. Here I've done it in 1 over meters, although later in this homework set you'll see me do it in 1 over nanometers. 1 over lambda is 1.097 times 10 to the 7th over meters. J is 2 and k is 4, so we have 1 over 2 squared minus 1 over 4 squared, and we get 4.86 times 10 to the negative 7 meters, or 486 nanometers. Now, because one of those transitions is to the n equals 2 state, the Balmer series equation works as well, and I'll show you this, that lambda, according to the Balmer equation, is 364.56 nanometers times the other state, in that case k equals 4, k squared over k squared minus 4. Plug in k equals 4 and that gives the same answer of 486 nanometers. Number 18. A ground state hydrogen atom absorbs a photon and ends up in the n equals 3 state. So n goes from 1 to 3, from the ground state to 3. The energy of the photon is the energy at level 3 minus the energy at level 1. We can use this equation. The energy is negative E naught, and E naught is that basic energy level that you can see given down below. So negative E naught over 3 squared minus negative E naught over 1 squared. You plug in the answers, and we get 1.94 times 10 to the negative 18 joules. Converting to electron volts, you get 12.1 electron volts. By the way, we could also, here I've written in burgundy, we could have said that E naught in electron volts times 8/9. Well, here it is, 13.6 electron volts times 8/9, and you get 12.1 electron volts. Number 20. What transition in hydrogen corresponds to the emission of an infrared photon? This problem is actually made easy because it's multiple choice. Without the multiple choice, it makes it a little bit difficult. But one of the hints is it says it's going to give off an infrared photon. So it's going to be a short energy. We use the Rydberg equation. 1 over lambda equals, and the Rydberg constant times 1 over j squared minus 1 over k squared. And here we don't know what j and k are. We can plug in, if lambda is 1282 nanometers, here's the reciprocal of that, equals, now I'm using Rydberg constant in 1 over nanometers. And so we get 0.071106 equals 1 over j squared minus 1 over k squared. At this point, it's easiest to just try different numbers. Try some simple numbers until you get what works out. However, here's something that'll make it a little easier to eliminate choices. And the key is that it says it's infrared. So let's look at this chart in the book. And we're not going to cheat and see the fact that it gives the answer right here. 1282 nanometers, but even if we didn't have that information, so that's the easiest to do, just look at the chart. Even if we didn't have that, if it's in the infrared, we can eliminate that n equals 1 because the Lyman series, those are going to be very large energies. Actually, energies larger than visible light. Anything in the Balmer series is going to be mostly visible light. We're looking for infrared, so n is going to be at least equal to 3. So and it could be n equals 4, transitioning down to that. But in solving for this, let me put the solution back up. As you plug in different numbers, start with one of the n values being equal to 3. Start with j being equal to 3, and just try different k values. And eventually you get k equals 5 is what makes it work. Number 21. For number 21, we have a transition in the hydrogen atom from n equals 5 to n equals 1. The emitted photon will be in what part of the electromagnetic spectrum? For such a long drop, you can look at the chart that I showed you in the book and see that it's going to be greater than visible light. But let's actually plug it in and solve for it. So 1 over lambda equals the Rydberg constant, I've got it in nanometers, times 1 over 1 squared minus 1 over 5 squared. And remember to take the reciprocal because you want lambda. So lambda is 105 nanometers, and that's ultraviolet. And you can consult the chart back in chapter 20 to show you that that's ultraviolet. Number 27. Alpha particles with kinetic energies of 7.7 megaelectron volts. What is the speed of such an alpha particle? Well, remember from last semester that kinetic energy is 1/2 mv squared. If we want the speed, we're going to solve this for v. V equals the square root of 2k over m. And we just need kinetic energy and mass in proper MKS units. If it's an alpha particle, the mass is approximately 4 atomic mass units. If you want to be more precise, you can look it up to get it exact, but this is pretty precise. 6.64 times 10 to the negative 27 kilograms. Kinetic energy, it's given in megaelectron volts, 7.7 times 10 to the 6. We need to convert that to joules. And once you have joules and kilograms, plug it in, you get 1.93 times 10 to the 7th meters per second. And by the way, that is about 6% of the speed of light. Number 29. Find the distance of closest approach for a 7.7 mega electron volt alpha particle. And in the book, in this section, there's an example very much like this. Same energy actually, but the book's example has the alpha particle fired towards a gold nucleus. And so you can follow that solution, but this one is towards an aluminum nucleus. We have the alpha particle far away, the alpha particle at its closest approach. It's going to go slower, 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 and then turn around and be repelled. We're looking for that turning point. There's its distance that we're solving for, and there's the aluminum nucleus. This is a conservation of energy problem. We have at the far away point, potential energy is essentially 0, kinetic energy 7.7 megaelectron volts. At its closest approach, where it's turning around, kinetic energy is 0. Potential energy is that Coulomb repulsion, K, and this is the K that we did early on in the semester, the 8.988 times 10 to the 9th, times the product of the two charges divided by R. We're going to set these energies equal to each other. This energy equals this energy. Eliminating the 0 terms, we have K0 equals U1 K0 equals K, charge of the alpha, charge of the aluminum divided by R, and then we solve for R, the distance. So we get the distance is 8.988 times 10 to the 9th times the charge of the alpha particle, the helium nucleus, is 2 times E. Remember, E is 1.602 times 10 to the negative 19 coulombs times 13E for the aluminum nucleus, divided by, I've got the kinetic energy of 7.7 mega electron volts converted to joules, and we get for the answer 4.86 times 10 to the negative 15 meters. So I've written 4.86 femtometers. Number 34. 34 says, what is the series limit for Lyman series, the Photon series, and the bracket series? So the series limit, how big can this get? How much energy can it be? Which actually is going to be the shortest possible wavelength. For Lyman, J equals 1. For the Photon series, J equals 3. For the bracket series, J equals 4. You can find those in the chart in your book. And the limit is going to be where it's coming from a very, very large state. So we'll just say K equals infinite. 1 over lambda equals the Rydberg constant times 1 over J squared, whatever J is appropriate, minus 1 over infinite, which is just 0. So it becomes 0.01097 over nanometers times 1 over J squared. So we plug in these J values and we get, for Lyman, 91.2 nanometers, Photon 820.4, and bracket 1459 nanometers. Number 35 is a very similar problem. Find the range of wavelengths seen in the hydrogen emission spectrum in the Photon series. The range of wavelengths means the highest and the lowest. For the Photon series, J equals 5, and K can be as low as 6 and as high as infinite. So we'll just do the wavelength equation twice, one for K equals 6 and the other for K equals infinite. Let's start with infinite to get the smallest wavelength first. This becomes 1 over 5 squared minus 0. That just goes away, and we have lambda equals 2279 nanometers. For the high end, we're going to do 1 over 5 squared minus 1 over 6 squared times the Rydberg constant. Lambda then is 7458 nanometers. So the range then is between 2279 and 7458 nanometers, and that's all in the infrared. Number 37. A hydrogen atom is in the n equals 2 state. How much energy is required to remove the electron completely from the atom? What is the wavelength of the photon? Well, what we can do is figure out what is the energy at this state. We can say energy 2 equals negative E naught over 2 squared. In electron volts, that E naught is 13.6 electron volts. Divide by 4, and it's negative 3.4 electron volts. It takes 0 energy. Notice it's negative. That means it's going to be bound to the nucleus. 0 energy is what would knock it free. So a photon of 3.4 electron volts being added to the negative 3.4 electron volts is enough to knock it free. We can also find the wavelength. 1 over lambda times the Rydberg constant, 1 over J squared, where J is 2. We're knocking it free, so let's just take it up to the infinite level. 1 over infinite, which is 0, and we get 365 nanometers. That is the wavelength of the photon. Another way to solve that is to do a relationship between energy and wavelength of the photon. We already found that we need 3.4 electron volts of energy. We'll need to convert that into joules to make this work, but we have Planck's constant times the speed of light divided by the energy, and that also gives us 365 nanometers. Number 39, according to Bohr's theory, how fast are these electrons in orbit? Find the speed of an electron orbiting at the n-1 level. Should relativistic calculations be used? Repeat for n equals 2. This is, according to Bohr's theory, the speed and the quantum number times Planck's constant over 2 pi, the mass and the radius of the orbit. We plug in those numbers where n is equal to 1. Planck's constant, the mass of an electron, 9.11 times 10 to the negative 31 kilograms. The radius at n equals 1 is 5.29 times 10 to the negative 11 meters. And we get 2.19 times 10 to the 6th meters per second. This radius, remember, is the Bohr radius. You can refer back to your book or your notes to see where we got that from. In part B, we'll have to figure out the new radius for the electron, but this is the Bohr radius. When we take this speed and divide by the speed of light, how we determine if we need to do relativistic calculations, generally speaking, if it's more than 5% of the speed of light. In this case, it's less than 1%, so we say no, it's not relativistic. Part B, n equals 2. We're going to need the Bohr radius, the radius of the orbit. It is n squared times the Bohr radius, which is going to be 4 times 5.29 times 10 to the negative 11. You can plug those into the equation, although by quick inspection you can see that in part A, this n becomes a 2, so it gets doubled, but a 4 goes down here, so it's going to end up being 1/2 of the answer we got in part A. And we can see that it's 1.09 times 10 to the 6 meters per second, which is even slower than part A, so that's not going to be relativistic either. The final question for this chapter, number 45. Find the minimum quantum number needed to make a hydrogen atom that is at least 0.5 micrometers in diameter. This would be a very, very large atom. Diameter of 0.5 micrometers, so the radius, we're going to cut that in half, 0.25 times 10 to the negative 6 meters. We use the equation that the radius is n squared times the Bohr radius. Solving for n equals the square root of radius divided by the Bohr radius. And so as we plug in those numbers, with the Bohr radius being 5.29 times 10 to the negative 11 meters, we get a quantum number of 69. And that's the end of the chapter 24 homework.